All right, it is Monday morning, March 22nd. We're reviewing for test 3, chapters 23 through 25. Don't forget it's over in the testing center this week, Tuesday and Wednesday, kind of a midweek thing. That's how the schedule fell this time. Homework 10 will be due tonight, even though pretty much finished all the topics already in 25. The aryl diazonium salt reactions, and now we'll do the electrophilic aromatic substitution on the aryl diazonium salt to form the diaryl diazo compounds. That's kind of a mouthful to keep track of there. And then, yeah, Wednesday, starting chapter 26, which is amino acids. So we've got quite a bit coming up there. Maybe let's start on the sideboard, Nick. And we've got some review problems ready to go here. And we'll go through these. And as a class, do them along with me. Try to stay ahead of me and maybe check your answer. And of course, questions and input, whatever you'd like to ask about here. So I have kind of a multi-step thing here, starting with cyclohexanone. And what's the first reaction? Chlorine, Cl2, and acetic acid. That should be what product? That goes back to chapter 23, I think. Yeah, so we're halogenating. The acetic acid helps form the enol. If you remember that, we can form enols or enolates under acidic conditions. We form enols. We can tautomerize. And that enol is nucleophilic enough to what? Attack the chloride. So what do we get here? We get the alpha chloro cyclohexanone. Okay, both sides are symmetric. So yeah, you don't have to worry about which side you're forming the enol. And then I think there's another step here, lithium carbonate, Li2, that's 2 lithium cations. So carbonate is CO3 double minus. You remember carbonic acid or your soda pop reactions from Gen Chem. Carbonic acid, if you release the pressure, it makes CO2 right away, right? Well, here's the lithium salt of that. It's not a super strong base, but it's strong enough to do what here? An E2 elimination. So we can get the eno. Questions on that? So far, so good? I see some people nodding their head, hopefully. It's very early, but hopefully enough to follow along here. And then we get into later chapter here. We get into chapter 24, I think, where we got the Malonic. Now, this is 23 also, right? The Malonic ester synthesis and the acetoacetate synthesis. That's right. And we've got methyl malonic ester here. And sodium methoxide. Remember, we use the base that corresponds to that. The pKa here in the middle is very low. What is it, around 10? There's a bunch of them that are 10. So that'll help you keep track. And in this case, that base, even though it's not a super strong base, it's strong enough to what? Irreversibly deprotonate there. Let's just form the anion so we can think about what's going on here with this reagent combination. And then what? We've got the Michael addition. Okay. So that's the conjugate addition there. That's a topic from 24, I think, yeah. And then we quench with water at the last step here. And so at this beta position, we have the 2 esters and the whole malonate unit incorporated there. Okay. And that's the Michael addition. Okay. And then what? Let's see. Water and acid and heat. So we're going to hydrolyze these esters. And that goes back to a previous section, right? That goes back to 22, the carboxylic acid derivatives. So you kind of see how these topics are building on each other. But there's something we can do with these malonates. We can hydrolyze that what? To the malonic acid. Okay. Now if we have water here and acid, we can hydrolyze that back. Methanol would be a byproduct, right? We have excess water. Sometimes we don't always draw that, but you can see hydronium ion. You have to be in water, right? So, hopefully we're clear enough on the test that you have all the information there, but sometimes you have to read into it a little bit, okay? And then the heat, definitely, around 100 degrees here. And then what can occur? We can decarboxylate, we're going to say, right? And we're still under acidic conditions, so we'll still have one acid there, and it will be protonated, but we just lost carbon dioxide. And we can review that mechanism if you'd like. Remember, we drew the different conformation here with the hydrogen right in between, and then we kicked the electrons around, and then we had to tautomerize. You get the enol form of the carboxylic acid toward the end, and that tautomerizes to this product here. Okay, so we get the ketone monocarboxylic acid. Questions on that one? Okay, so far so good. All right, a little bit of a twist here, different base. Sodium hydride, same substrate, cyclohexanone, forming now an enolate, right? Not an enol. This over here was enol, right? But now we're doing enolate. And how do you know that difference? Well, you've got a super strong base, right? Sodium hydride. The byproduct, the conjugate acid, will be hydrogen, H2. And that has a pK of what, 38? Okay, very high, very super weak acid. So you know its conjugate base is super strong, okay? You can form the enolate, and then what? Ethyl iodide, we're going to form the ethyl ketone, right? So we're going to do an SN2 reaction on that primary alkyl group, and the enolate is now the ethylated product, okay? Now, LDA, lithium diisopropyl amide, again, a super strong base, but also what is LDA? It's also strong and what? Bulky, right? So in this case, we've got two different places to form the enolate. So we're going to form where? The enolate on the left side. That's the less sterically hindered side. And this is, again, an irreversible deprotonator because it's such a strong base, right? So we'll just have the enolate here. We can do it at low temperature. We call it the kinetic enolate, in that it forms faster at that less hindered spot. This would be the thermodynamic enolate, right? If we use sodium hydride here again, we'd actually form the enolate over here, okay, the more stable one, because it's smaller. It can get in there and grab that. But LDA just grabs that one, and then we methylate. So what's our ketone product in this case? Well, the ethyl's still over here on the right, and we have methyl on the left, okay? So we call that regioselectivity, which region of the molecule gets functionalized. And depending on the base and how we use that, we can get different products. Okay, question on that? Yes, please. On this side? So the question is, could we put a methyl group on the right side instead? Right. Or, well, let's say, okay. So the question is, could we put a methyl group on the right side in addition to the ethyl group? Okay. Yeah, so if we used the small thermodynamic base here on this ethyl ketone, right? And then we, put in methyl iodide, the same alkylating agent. Look, now we would form the enolate right here, right? And then we get a different product. We get the isomeric product. We'd still have the ethyl there, but now our methyl would be there also. Was that what your question was about? Okay. Yeah, and you see we've got different reagents, and if you just change the base, you can change the product there. So very good question. Yeah. Let's see. What's our next one here? We have ethyl acetate. And we're treating with sodium ethoxide in ethanol. Notice I'm not drawing the solvent there, but the solvent would be ethanol. Let that react for a while, and then we quench with HCl, dilute HCl. We're not heating it up, not decarboxylating. Decarboxylation only when we have heat at the end, and hydrolyzing, right? But here we're just protonating what? And by the way, sometimes we think, well, this is the Claisen reaction. You think we need two of them there. Well, no, you have an amount there. You're just going to react. One is the electrophile, one is the nucleophile. And what? We're going to get the dimeric product. Okay, it's not symmetric, though. What is it? It's the ethyl acetate. Okay. And that is the Claisen product, right? Initially, we formed an enolate here, and then we used that as our nucleophile with another one of these esters as the electrophile, right? We got our tetrahedral intermediate. Don't forget about that. We could review that mechanism. That breaks down. You generate ethoxide right in the presence of this. This is the breakdown product of the tetrahedral intermediate. But as soon as that's formed, ethoxide takes off that proton. So we have to have a proton source at the end to neutralize it and get our product out. If we don't, if we put in water and just wash it out at that point, our product will stay in the water because it'll be the deprotonated version of this, okay? The base is strong enough, we'll just deprotonate. So this protonation step is unique, I'd say, to the Claisen in that we have to put that proton on carbon here to get the neutral product. You know, we've used water in the past with Grignard reactions and aldols just to protonate an O minus, you know, to get the neutral alcohol product. But here it's a little bit different, right? Here it's that pKa in between the two where it's very stable, pKa of 10, whereas an alcohol, pKa is 16, 17, right? So there it's a little easier to protonate, but here, because it's so stable, resonance stabilized, it can stay as an anion until we protonate it there. Question on the Claisen, we could review the mechanism. We'll see that in some of the other problems here in a minute, I think. Next reaction, sodium ethoxide again. Reform the anion there, and then what? Alkylate with allyl bromide. So we'll get the same thing, ethyl acetate, but now with an allyl unit right there, okay? And it is right in the middle there, okay? We played some tricks with this. We showed that if you use two equivalents of a strong base, you could actually form the dianion, and then you can alkylate selectively on this end position. I think that's one of the harder problems, write-on problems on the sample test. Or was it a worksheet problem? I don't know. We'll see it. We'll see it later on. But there's some variations of that should be aware of. And now here's acid and heat. So what are we going to do? Hydrolyze the carboxylic acid, and then decarboxylate, and then tautomerize. And what's going to be our product? A ketone product, okay? And that is the the acetoacetate synthesis process, where you start with this Claisen product, right? That we learned about before in chapter 23, okay? But here's how we make it in 24, right? The Claisen reaction. The alkylations can go and then decarboxylate. Questions on any of that? All right, let's get a few more problems up here, and then we'll go back to the overhead and finish off these aryl diazonium couplings. I think we're okay on that. How about this reaction? Sodium hydroxide with an aldehyde and heat, 100 degrees. How about this one? Speaking of LDA, and an aldehyde, and then quench with water. Let's see, how about this one? Got a diethyl ester and sodium ethoxide, and then quench with acid. And how about this one? An aryl ketone and an ethyl ketone with sodium hydroxide and heat. Okay, there's some more variations of carbonyl enolate chemistry, right? So let's see here, sodium hydroxide just with the simple aldehyde. What are we going to get here? Well, it's going to dimerize again, right? Similar to the Claisen. One's going to be the enolate, one's going to be the electrophile. And we are at high temperature, so we may want to think about this sequentially. What are we going to get first? Well, we're going to get an aldol product, okay? And that is the intermediate for the aldol condensation, which is what these conditions are. At higher temperature, what do we mean by the aldol condensation? We have the ability to, what? Further react this product and form not the alcohol here, but what? The alkene, right? So the aldol condensation is going to occur there. And the temperature lets you know that that's going to occur. Now, it's fundamentally different than the Claisen reaction, right? That's with esters. And that's where the tetrahedral intermediate can collapse and kick off ethoxide. Here with an aldehyde, you just have a hydrogen there. We can't kick off hydride. That's a terrible leaving group. Way too basic, okay? Now here, eventually, with a higher temperature and more base, we do the E1CB. If you remember that mechanism, which is the variation at the end, we can review that as well. But right now, we're just focused on reactivity, the different conditions, and the different types of products. Questions on that one? All right, how about this one? LDA, we're going to form the enolate on which side? The right side, okay? And it's going to condense with acetaldehyde, and that will give us O. It'll be minus at that point. And look, room temperature just quenched with water. So we're not going to eliminate it this time. We're just going to get the aldol product. We call that a directed aldol reaction in that we have an unsymmetric ketone. And with LDA, we can form this enolate selectively. And then that, you see, adds, just to add on a little on the mechanism. Hopefully you can see that. And then the water just protonates there. Yes, question? Yes, the question is, can you do a directed aldol reaction with sodium hydride? The answer is yes. It would be on the other side in this case. So you see some of the flexibility you have. And again, we're not at higher temperature. That's the other key thing here to notice. So we got this. And don't worry about stereochemistry. We actually have 3 stereocenters here. That's an advanced topic to keep track of those kind of things. I think I showed you an asymmetric enolate, the Evans alkylation. Just gave you a little taste of that, and that creates 2 different diastereomeric transition states. Because it is a chiral molecule, it allows you to form one stereoisomer over another. But in this case, for our class, we'll just stick with the connectivity and the reactivity there. There we go. Here we got a diester. So one will be the nucleophile, the other will be the electrophile. And that's kind of the tricky thing to do with these intramolecular examples. And this is just 2 esters. We've got 2 different types of ketones here. Oftentimes the tricky part of these type of problems is identifying which one's the nucleophile, which one's the electrophile. And then follow through with it and use your scratch paper and figure it out. And depending on what the question's asking, you know, it may not want the full mechanism. Sometimes we just have that reactivity sheet where you just supply the product or the reagents, whatever. So there's different ways to approach it here, but identifying which is important. And you see we'll get our tetrahedral intermediate there. That will collapse, and you'll get the intramolecular product here, and it is just quenching with dilute acid at room temperature. So I think we just made that bond right there. Here was our electrophile, and here was our nucleophile. Okay, so we did have a tetrahedral intermediate there. Did we have the right number of carbons? Yeah, I think so. 1, 2, 3, 4, 5, 6. Yeah, 6-membered ring. Count carbons, and that'll help you with the ring sizes. 5-membered rings and 6-membered rings are always best for these type of intramolecular reactions. Okay. Let's see this one, same analysis here. We're using sodium hydroxide in this case. So we could have the nucleophile here and reacting here. That would be a 4-membered ring. Maybe not. Maybe consider some other spots. If we have this enolate and attack there, still a 4-membered ring. But what about this one here? If we have our nucleophile there and then consider what our electrophile here. That looks good. 1, 2, 4, 5, 6. Okay. And let's see. We are at high temperature here. So what are we going to get? Well, we're eventually going to get this then. Okay. And yeah, these products seem a little jarring at first, sometimes when we see these. And there are a bunch of great homework problems at the end of this chapter. If you work through a few of those, you should be okay seeing this. But we just made that bond right there. Higher temperature, so this is the aldol condensation. We had, we've got a ethyl there, don't we? 2, 3, 4, 5, 6, 7. Yeah, 4, 5, 6, 7. Yeah, that's why I always count carbons, just to make sure you don't lose any of them there. But yeah, so here was our electrophile, here was our nucleophile. And yeah, I think you can go through that and push electrons. Question on that one? Yes, please. Couple. Go ahead. Ah, yeah. What's the difference between these two? This is what reaction? This is a Claisen. Well, so the question is, what's the difference between these two? Because they look similar, right? They're enolates, you could say. The enolates form of ethoxide here because it's the ethyl ester, and then we get a tetrahedral intermediate when we react with this electrophile. Okay, that'll give us a tetrahedral intermediate right here. That'll break down and give a ketone there. Whereas here, when our tetrahedral intermediate breaks down, we had an alcohol here. Okay, and that's the main difference. So the aldol, the initial aldol reaction gave an alcohol here, and then the heat here and more base allows for the what? E1CB to take over. And that's the difference here with the aldol condensation. Was that a similar question? Yeah, so this is kind of ambiguous. I added acid just to protonate here. If you have hydronium ion, water, and then heat, then we're going to hydrolyze this, okay? So if we're just using, well, what did we say before? We said dilute HCl at room temperature. There's the full conditions for that. And that's just protonation without decarboxylation after hydrolysis, yeah. So there's some timing there. You know, the ester doesn't fly off instantaneously with acid and water. It does take a little while. So you can protonate here just for a few seconds. You're just protonating here. And that's very fast, okay? Then we stop that reaction. We, you know, work it up, extract it with ether or hexanes, and then this is away from the acid. So it's only exposed for a minute or so, yeah. But that's kind of a practical operational thing. But that's a good question to think about. And hopefully this will be clear, you know, what we're talking about. If we said, you know, concentrate HCl, water, and heat, then we'd want to do the decarboxylation thing. Yeah, okay. But that's a good question. Okay. Let's see, should we do a couple more here? And we will get to the test, don't worry. How about this one? Let's see, make this. And I always like these kind. And this came out of a problem we saw before with one of the barbiturate drugs. So how do we make that? And how about this? How about a mechanism of this? We're going to take acrolein and a diethyl ketone, I think. Yep. Sodium hydroxide and heat. And this is kind of a simplified Robinson annulation, kind of stripping it down to the basics here. And I'll give you the product. And the problem here is provide the mechanism. Make sure I got all the carbons there. I think I do. Let's see. Do I have them all there? No. 1, 2, 3, 4. 2, 3, 4. 1, 2, 3. Yeah, there we're okay now. Yeah, methyl vinyl ketone. And that's so the mechanism here. Okay, so a couple different types of problems here. How do we make this? Well, can we think about this? Can we do the malonic ester synthesis there? No, because this is an aromatic benzene there. It's sp2 hybridized. We can't do SN2 there. Remember the alkylation, the malonic ester synthesis. We need primary or secondary halides, or good leaving groups, right, for an SN2 type reaction. So how can we do this? Well, we can also make this bond here, right? So we could have this methyl ester already with the benzene on there. And we could think about making that, depending on how the question's asked, you know, we could, you know, put this together and do some other things there. But how do we put that on there then? Well, we need to treat with sodium methoxide. That will form the enolate here. And then what do we need? Well, we need a carbonyl with a methyl there. So what about this? This chloroformate, it's called. And if we have that chloro there, you see our tetrahedral intermediate would have a chloride option as a good leaving group. And that could break down and give us the malonic ester, but indirectly, right? Not from the malonate, because we're limited by the phenyl group here. And I think we showed before how to make that. You can make it from the carboxylic acid. You make that from the primary alcohol. You make that from a Grignard and the epoxide. Kind of go through that. Will there be multi-step synthesis problems where you got to review a lot of problems from the past? Well, maybe, especially with the aromatic ones we'll see coming up here. Don't forget those electrophilic aromatic substitution reactions. We can use those in conjunction with the aryl diazonium salt idea. So those might come up. But here the key idea we're pointing out is the limitations of the malonic ester synthesis and using a different acylating agent. Okay, so those possibilities are there. Okay, what about this one? How are we going to do this reaction? Well, look, we've got methyl vinyl ketone. That can be an electrophile, what, at the beta position here, right? It can also be a nucleophile right here at the methyl position. So just kind of analyzing what we've got here. Let's see, this could be a nucleophile here, and this could be an electrophile here, right? And you kind of see all of those relationships in this target molecule. So which thing are we going to do first? You could actually do this a couple different ways, but remember we learned what? The Robinson annulation by way of first doing what? A Michael addition, a conjugate addition, and then what? An intramolecular aldol. So that's what you kind of see here. Let's do this first here. This will be our Michael addition, and then our aldol will be right here, okay? And this is a stripped down version, so it's actually a little simpler than the ones we did in class. But let's do the mechanism here. So we can form the enolate there, sodium hydroxide. So yeah, I'm abbreviating it a little bit. Show the deprotonation step if that's part of it. And then we'd get this, where we'd have the enolate added there, and we've got a new enolate up here, okay? So yeah, verify that that's the product of the Michael addition, the conjugate addition. And then what do we need to do here? Well, we've got water, and we're just going to protonate. And, we could just isolate that Michael product, okay? And depending on the condition, oh, this is an ethyl group. I keep losing carbons. Okay, yeah, you guys need to watch me here a little carefully. And now, in order to do the aldol, we're going to have to what? Take off that proton. So we'll have this enolate, and yeah, okay. And there's a lot of places we could form enolates, right? We could form enolate over here, here, and we'd get different size rings and stuff. But look, this one right here leads to this product. In this problem, you're given this product, okay? So some of these harder mechanism problems, we always give you a product, and then it's just a roadmap that you need to do to follow that. But you see, leading this 6-membered ring, so that's probably favored. You probably get a good yield for this reaction. And then what? Bring this down, attack there. That will give us the 6-membered ring. And we'll see, O minus, and that there. And so, yeah, we got the 6-member ring. Now what do we need to do? We need to do the protonation here, and then we need to do the E1CB. So let's see. And then, yeah, let me just jump ahead. Form the enolate again, right? And you can show the resonance structure of that. Don't just do the deprotonation and the elimination right away. Show the enolate and then onto the product there. I think that's everything. The ethyl group's still there. Yep, there's where our ketone, that was the electrophile in this case. Notice the ketone here started out as a nucleophile to do the conjugate addition. So it's a double type reaction in that case. Questions on that one? You okay on that one? All right, let's do a couple of amine reactions. And get the sample test in some of these aryl diazoniums. So let's see, how about this one? Cyclopentanone and diethylamine and sodium cyanoborohydride. And how about this one here? How do we convert this into this? And this kind of picks up where we left off last time in class. How do we get the tribromobenzene where they're all meta to each other? Okay, work on that one there. And how about, a couple more here. Let's get phthalimide up here. For the Gabriel synthesis, we're going to deprotonate with KOH, and then we're going to add this bromide, and then we're going to add hydrazine. And what's the product? Two-step synthesis there. And let's see, oh, one more. How about an acid-base problem? Here's a substituted pyridine. I'll even draw the lone pairs for you. And we're just going to put in one equivalent of HCl. What's the product? Got two amines, right? One equivalent. Where is that proton going to go? Let's see. Let's do this one first. We have diethylamine with a ketone. So what's that going to do? It's going to form an iminium ion. I guess we could draw on here, give you the intermediate. So use the mechanism to help remember, what's going on here. Iminium ions are intermediates on both the imine formation and the enamine formation. Secondary amines will give enamines with the double bond between two carbons. But in this case, the sodium cyanoborohydride intercepts that electrophilic iminium ion, and it's a way to make then what? Amines. Here we go from a secondary amine to a tertiary amine, okay? And this reductive amination is an excellent way to make secondary and tertiary amines, okay? From aldehydes or ketones, okay? So in this case, it's a ketone with secondary amine, so it goes to that tertiary amine in that case. Question on that? Yeah. Okay, what about this one? What are we going to do with aniline? How do we convert aniline into a good leaving group? Well, that's with HONO. And you can just write that. And that's what? Nitrous acid. And that will form the aromatic, what? Diazonium salt. Okay? Or you can write sodium nitrite and HCl. Okay? That's usually how we do it. It's more convenient because that's a salt and HCl is cheaper, whatever. So that's what we'd usually get, the chloride aryl diazonium salt. And then what do we do here? Well, we could just take this off with H3PO, H2PO, H3, sorry, PO2, and that would give us our benzene back, okay? But before we do that, we want to put on 3 bromides. So instead of doing this right away, what can we do? Brominate. And aniline, remember, is a very good electron donor because of those lone pairs. You don't actually need the ferric bromide in this case. You can do electrophilic aromatic bromination on phenols and anilines without it. And if you have excess here, you'll actually make it go on all the spots, the 2 orthos, and the para. You get a very good yield of that. And notice they're all, what, 1,3 to each other. because those are the ortho and the para positions here. Then we treat with HONO, and in this case we get the tribromo aryl diazonium, right? And then we treat with H3PO2, hypophosphorus acid, and that reduces the nitrogen down to the hydrogen. But, you know, we use that as a directing group to do other reactions first, and then we cleanly took it off. We could not make this directly from benzene using bromination because they are orthopara directors. After we had one on, we could get one, we could put multiple on, we'd have to use the iron tribromide, and then we'd give those different products there. All right, let's look at some other synthesis problems here using the aryl diazonium. And this points out the utility of that reaction used in conjunction with some of the other electrophilic aromatic substitution guys. So how would we make this aldehyde, benzaldehyde with a bromide here? Well, we haven't shown you how to make aromatic aldehydes yet. You know how to make aldehydes from a couple different ways. From esters, we could make it from a benzoate ester reduction with diabol, or from a cyanide, but those are all electron withdrawing groups, and here we need the bromide at a para position. So we need to think about that as some sort of an electron activating group, right? So here we could start with this thing brominated, and we could use nitric acid, sulfuric acid, to put the para-nitro group on there. And, you know, why are we doing that? Well, that nitro group will now become the aniline, and then we can eventually convert that into a cyanide, and then eventually reduce that to the aldehyde. So what do we do at this point here? We would have to hydrogenate with palladium and hydrogen, or we could use HCl and tin here to get the aniline now. And now what do we do with the aniline? Well, HONO, and that will form our aryl diazonium with the bromide still there. And we know a reaction to put on a group that could become an aldehyde here. Yeah, it's this copper cyanide reagent, okay? Remember, we had a bunch of nucleophiles there, and there they are if you're here live and you know, review the outline for the chapter. You can see all those Sandmeyer reactions they're called. So copper cyanide can go on there now. We can get the cyano, which notice, you know, that's an electron withdrawing group. That would be a meta-director, okay? But here we need this para-bromo aldehyde. And then how do we get that? Well, the cyanide can be treated with diabol, diisobutyl aluminum hydride, remember? Then quench with water, and that will give us the product, the aldehyde at that point, okay? So that's one way to form aldehydes. We could form aldehydes from the oxidation point of view. If we had a benzyl alcohol with PCC, we could form it. But this way, with the Sandmeyer reaction, that copper cyanide with the aryl diazonium lets us do that directly. Okay, here's another hard one. How would you make fluoride with an ethyl group there? Okay, so this is the only way we know how to make the fluorides now, with the hydrotetrafluoroboric acid. And notice it's meta to this ethyl. An alkyl group is an orthopara director, right? And so are the halides. So obviously there's some different things we need to do here. Let's start with this guy, which is acetophenone, right? And that is indeed a meta director. So we can nitrate now. So that's chemistry from what, chapter 19, whatever. And we couldn't do the Friedel-Crafts on the nitro, so we had to nitrate after we did Frito crafts with benzene to put that on, right? No Frito crafts on highly deactivated things like nitrobenzene. But now you see the meta relationship, but we've got to transform both of these, right? So our first thing here is H2 palladium and then HONO. So I'm kind of combining a couple things here. So we'll have the diazonium, okay? And now we can treat with the hydrogen tetrafluoroborate, okay? And that's the reagent to put on the fluoride. And then I think you see we've got that meta relationship. And what do we do with the methyl ketone now? Well, there's a couple things we can do there. We know how to reduce aromatic ketones to the alkyls, right? And that's the Clemmensen. We could do that one. Or what? Wolff-Kishner. And remember what those reagents are. Clemmensen is what? Hydrazine and HCl. And what's the Wolff-Kishner? That would be the hydrazine and the, the Clemmensen is HCl and zinc, right? Zinc amalgam. And then the Wolff-Kishner is the hydrazine and base, hydroxide, potassium hydroxide. Either one of those would reduce that down to that position there. Okay, so that's a couple of reactions that show you the utility of it. Now I'd like to wrap up with the aromatic electrophilic substitution that these reactions can do. And that's this reaction. So you can take these aryl diazoniums and let's draw out the Lewis dot structure. And let's react this with anisole, okay? So these are strong enough electrophiles that just on their own here, what are we going to do here? Well, we can have these electrons come out and flow in here. Here's our new electrophile for an electrophilic aromatic substitution reaction, okay? So let's see if those electrons flow the way we do. And what, this is a donor group, right? It's an ortho-para director. So we're actually using it correctly here. And if we flow the electrons that way, what do we get? We get the benzene here, get a pair of electrons on there, and we get our aromatic group here. And that's what, our allocation that we saw before, right? And so what do we need to do here? Well, chloride or some other weak base can just take that off, and you see we get the stable now diazo compound. And these are fully conjugated things. They tend to be colored, a lot of different colors here. I think this one has a yellow color to it. We could have had an aniline here or an amine of some kind, which would be a strong donor. This works better with donor groups here, but you can do other reactions with that to form these diazo diaromatic compounds. And yeah, sorry, we're running out of time here. Let's go to the board here and go through a couple of these real quick. Oh, well, I'll just show you the food colors. You can see the red here and the yellow. Here's butter yellow, you can see. So that was made from the dimethyl aniline and the benzene diazonium salt. There's some others here that are known there. Let's go to the sample test now. Sorry, we're not leaving much time. Questions. Let me jump right ahead to questions that you guys might have on this. And I do have the one with the key here on it, so you can kind of see. I think that first page is kind of straightforward. Naming, we only have the amines as a new thing to do naming. If that's on there, it would be pretty simple. Select the position of deprotonation or different types of reactions we can ask about. Different intermediates, asking about intermediates here. Here's an application problem, the barbiturate drugs. We made those from the malanates and urea. They had urea, which is that diamino ketone there. So know the basics of that. You know, not everything about how those drugs work or the applications or anything. This one's a little tricky because it's an intramolecular aldol condensation, right? So we're giving you the conditions there. And I think that's good to count carbons and to think about what's connected to what there. Usually it's not too bad. And this is another intramolecular, so there's two intramolecular aldols here, okay, which is not a resonance form. So that's this one here. There's implied here to have a hydrogen right there, so that's incorrect, okay. All these others are resonance structures of that Claisen intermediate, right? That's the Claisen intermediate there. This one, we kind of talked about that. All of these can be readily made. No, this is the only one that can be. Here's that problem we were just talking about. If the aromatic group's right on that position, you can't do the malonic ester synthesis. Same thing here, okay, and here. Okay, so there are limitations to that. Malonic ester synthesis, we need an sp3 hybridized carbon at that position. And we need groups that can come on from SN2 type reactions, right? Okay, and aminium ion, yeah. There's the electrophile of the aromatic diacetization reaction. The HONO reagent makes that nitrosyl cation, okay? Not the nitronium cation, that's for nitration. That's from nitric acid. This cation is from this nitrous acid, right? One less oxygen. Okay, the fluoride, we just talked about that. Oh, here's our position of protonation. We skipped over that. Which one will be protonated here, the pyridine or the amine? Sorry, we left that one off. Come back over here for a second. What's this problem right here? So what do you come up with? Is this primary amine going to get protonated, or is the pyridine going to get protonated? What are the pKa's here? An alkyl amine is around 10, 9 or 10, right? Remember the pyridinium cation? What's that? That's 5. So what? This is the stronger acid, which means what? This is the stronger base. So with one equivalent here, what's it going to be? It's going to be that. Okay. You're going to need another equivalent of HCl to protonate that. Okay. So that's kind of the similar thing here with the this problem. Sorry, I'm making Nick move all around there. We'd want to protonate right here, right? Because that's a pyridinium type lone pair here. This is a pyrrole type lone pair. Okay, so that's not a good base because the lone pair is in the aromatic grouping there. Haloform reaction, yeah, 20 there. Okay, so here's typical, you know, what we'll see on the test, right? And those are the standard reactions. Make sure you understand the basics of that. Most of them are one step. We got a couple two-step things here. And hopefully it's clear here how we're quenching things. I think so. Or what the temperature is. Questions on any of those? We're okay. Here's another way to ask questions, to have you fill in the reagents, right? And some of those are multiple steps, but we've done a bunch of examples like that to help review for that. And we got the HONO reagents down here. There it is right there. Okay. This one is just forming the amide, which lets you do the Friedel-Crafts and then hydrolyzing the amide. That's just a variation we kind of talked about. Reductive amination. Oh, that's that same problem right there. And the regioselective alkylation. Now for a couple problems, here's a intramolecular aldol in the conjugate addition. So this is a Robinson annulation variation. Here the tricky part is you've got to alkylate first with ethyl iodide, and that ethyl group, see there, goes along for the ride. It stays at that position. And you reform the enolate in between, and then do the Michael, then you do the aldol. Okay. Notice we're under basic conditions, so everything is negatively charged. That's another way to check your mechanism. You're under acidic conditions, you want things protonated, and they're going to be cationic if they're ions, right? Under basic conditions, you're going to have anions. Here's a synthesis problem using reductive amination. There's many ways to make this tertiary amine. We could have done reductive amination on any end here, but you're kind of directed. You're given these starting materials. You're told to use those. So I think we start out with an alkylation, decarboxylation, hydrolysis to give this ketone. And you see that ketone's right there, right? So we need this amine, this secondary amine, to do a reductive amination. And you're given this bromide right here. So the Gabriel synthesis gives that primary amine. And then let's see, oh, reductive amination here. Oh, doing 2 reductive amination. We could have done an alkylation, you know, but this is a little more secure, I think, there for that reaction. Questions on that synthesis? Yeah, and here's a harder problem. This one really, you know, you look at that and you say, well, we haven't done anything like that. Well, you see a lot of carbonyls there, right? You see ester here, ester there, and ester, 3 esters. And you see 3 esters in the starting material, but this epoxide obviously has to go away. Here, I think the idea is do what you know how to do. And so what is this? This is malonate. So we've done malonate where we form the anion, right? And then we've alkylated. Okay, so there's a primary bromide. So getting to here is kind of logical, I think. The next few steps is kind of a stretch, right? So reform the enolate. Oh, open up epoxides. We've opened up epoxides before, okay? So maybe that's not so much of a stretch. And that does form this 5-membered ring right here then. And then what? You have this O minus here. The epoxide opens up and gives an alkoxy group. You can kind of see that can bite back new tetrahedral intermediate. And if that breaks down, you go directly to the product. So there you require some insight and maybe, you know, try it with your scratch paper. Get to some intermediates that make sense and then try some logical things. And make sure you're following the logic of different reactions we've already taught you. Don't try to invent something new. Counting carbons and then following the principles is what's going to help you out there. And I'm sorry, running out of time there. You got questions? Zoom into office hours or email me. TAs have review times also, just on their own outside recitation office hours, whatever. You can get a hold of us that way. But yeah, good luck on the test. And remember, come prepared on Wednesday for chapter 26. Peptides, proteins, yeah, we'll start amino acids. So very good, thank you.